Hello, Glorious Cow here. This is an instruction cycle log from MartyPC. I have published this trace log showing the execution of 8088 miles per hour CPU test. I published it with my last blog article on that CPU test, which I will link in the description. But some people have told me that the cycle log doesn't make a lot of sense without context or some bit of explanation. So this video intends to go through the cycle log and kind of explain what the columns are, what you're seeing, and how to interpret it. Now, the first thing to really know is where instruction boundaries are. You can see over here in the info column, if you see a disassembly, this is when an instruction is beginning. This indicates that an instruction byte has been read out of the queue and is beginning. And if you see the word execute, that means that microcode execution has begun. Now, if we come down to something like XOR we'll see that the execute didn't happen at the same time that the instructions started. Now, why is that? Well, it's because we had a mod RM byte, and the microcode execution does not begin until after the mod RM byte is fetched. So sometimes you'll see execute happen on the same line that an instruction begins, and sometimes it'll be delayed a little bit, usually depending on if there is a mod RM or if there is an EA operand to fetch or anything else that will delay microcode execution. So basically you can time instructions between disassembly output here. So this is the entire execution time of the move AL 12H instruction, because the very next instruction begins the out, which then executes until the next disassembly. So this is how you tell what instructions are what. Out instruction is going to execute until RNI end, and then the move instruction begins, and then that executes until XOR BX begins. So let's look at the columns in order and see what they're doing. The first column is cycle number. This is actually the linear cycle number since the CPU is reset. If you're taking a cycle log from MartyPC in the middle of a program execution, this number could be quite large. Consider that it will go up by 4.77 million every second. Since this trace was taken from just right after CPU reset, this number is actually pretty reasonably small. The ICN column is the instruction cycle number. This is the similar counter, but it is reset to 0 every time an instruction begins. So you can see here, it's counting up to 9, but then when we begin the out instruction that immediately follows the move instruction, it is reset back to 0. The third column here is the ALE, or address latch enable line. What's the address latch enable line? Well, the 8088 had to fit into a 40-pin DIP package. That means we had a kind of a scarcity of pins to use. The 8088 has 20 of those pins assigned to address line. That means that we had to reuse some of those pins. On the 8086, you had 16 data bus lines. On the 8088, you only have 8. But in any case, we had to reuse those pins between address pins and data pins. So the ALE line is a signal to the motherboard to take the address lines while they are valid and store them into address latch buffer chips. So that's done when the ALE signal is high. And then that corresponds with the next column, which is the address latch enable value. So this actually stores the value of the address line for the entire M cycle. So you'll see that it stays the same value until the next ALE line is high. If I showed you the actual value of the address lines, they would become invalid the moment that ALE went low and those pins start to be reused for status and data and other things. The next column is the segment status readout. And this again is reusing those pins to indicate what segment is in use. Now, you know the 8088 uses segment offset addressing. So this is kind of a helpful clue what segment is being used to calculate that segment offset. So we can see here that this is CS, meaning code segment. So we know the address over here is a combination of the code segment and the program counter. The next value here is M flags. These aren't actually status lines off this 8088 CPU at all. These are off the Intel 8288 bus controller, which reads this segment, the status lines S0, S1, and S2 off the 8088 in maximum mode to compute bus signals. This R indicates a memory read flag operation. And then you have the corresponding signals for I/O, which we will skip for now. The next column is our DMA status. This is kind of a artificial emulator output. It doesn't have anything to do with the CPU's outputs. This is just the debugging information so you can track progress of DRAM or DMA refresh. What these two numbers are actually the pit counter and the scheduler for the pit channel 1, which drives DMA. We'll look at that later. The next column is the bus type. These are, again, the status lines S0, S1, and S2 that are fed to the 8288, which indicate the bus type in progress. In this case, we have a bus type of code fetch. This allows us to know that, oh, a code fetch is in progress. The next column is the T state. We should know what a T state is. A complete memory cycle is called an M cycle. An M cycle comprises of T states from T1 to T4. So we go from T1, T2, T3. We would proceed to TW if there were any wait states. There are none in this case, so we proceed to T4. And then these 4 cycles complete an entire memory bus operation, or M cycle. The next column is the data bus. This is also, again, only valid when we have read or write signals from the 802 to 88. We can see that we made a read request on T2. This is a read request from memory. The data bus lines become active, but they don't have the value that we requested yet. We have to wait until T3 before memory has a chance to respond. Now memory could have said, I don't have enough time, and inserted some wait states. In this case, it did not. So we have the value 12 on the data bus line at this point. Now, you know, that value 12 is the immediate from the move ALOX 12 operation. So that 12 is then pushed to the instruction queue over here. The queue column is the contents of the instruction queue. So it's read out here and placed into the queue here on T4. Now these two columns are some internal bookkeeping that MartyPC does. Over here we have the BIU state. This is kind of something unique to MartyPC. I kind of figured out at least my mental model of how the BIU operates as a state machine. And I will link the blog article in which I describe that state machine in the description. But this has some few states, basically PF for prefetch, EU for service EU, or an intermediate state where it's transitioning from one to the other. It can also go into the idle state, which we might see. And the next column is the prefetch state, basically telling you what the prefetch is doing or thinking about doing. In this case, if it's in progress, we are actually performing a code fetch. If the state is scheduled next, then the prefetcher has decided to perform a prefetch at the end of the current M cycle, because it can't do it in the middle of an M cycle. So what this is saying is that a prefetch is scheduled to happen on the next M cycle. Over here we have queue operation. These are again status lines QS0 and QS1 off the 8088 CPU pins. And this indicate when a queue operation has happened. We have 3 possible statuses here. F for first byte fetched. This indicates that the first byte of an instruction has been fetched. Or potentially a processor prefix, like the instruction segment override prefix will also come in at the first byte. You can have multiple first bytes per instruction as long as they are prefixes. So we can see here our F, which is not a prefix, usually corresponds with the first cycle of execution of an instruction because we have a byte read and ready to execute. Unless there's a mother M, in which you have to wait for the subsequent byte to be read. So down here we have an S. This does indicate subsequent byte read. In this case, this is the OH immediate, which is over here. When we have a Q status line that is not idle, we will see the value that was read at that for that operation over here in the Q data line. So here we have a byte put into the queue. It's actually read out on this cycle, which is why it disappears. And then we have the Q status lines reflect the operation that was performed on the previous cycle, showing that the 12 was read out as a subsequent operation. So let's start looking at how these instructions work. We have the move instruction here. Now move is going to read an immediate, which is 12 here. So that code fetch occurs on this M cycle of T1 to T4. It read the 12, it put it into the queue, the EU read it out, was reflected in the cycle, the queue operation, Q status lines, and then the instruction ends here with RNI. RNI is a microcode flag. It stands for read next instruction. It's executed when the microcode has completed execution of an instruction. RNI will instruct the CPU to do a few things. It will check the interrupt request line. If there is an interrupt pending, then the interrupt will be fired at that point. If there is no interrupt pending or interrupts have been suppressed or the interrupt flag is not set, then we ignore interrupts and we proceed to fetch the next instruction. Now, you'll notice that the queue is empty at this point. We don't have an instruction byte to actually begin, so we have to wait. This is a code fetch M cycle. These 4 cycles here are in process of reading E6, which is the next instruction byte. That's read into the queue and placed into the queue on T4. So we now have E6, which is the out opcode, and it's put into the queue. It is then read on the next cycle. Remember, it takes 1 cycle to read from the instruction queue. So now we have E6 read from the queue, and the next instruction can begin now on this cycle here when out executes. Because we fetched the first instruction byte of E6, out can begin. It has no mod or M to wait for, so it can immediately begin microcode execution. So out is kind of interesting. We see a few more status lines. Let's skip ahead. Well, let's come down here to when the EU actually requests a IO bus transfer. That happens on this cycle. We can see the notation here, bus begin, indicating that the microcode for out is attempting to do a bus IO write. Now, if we look and see what status we're in T4. That means that we can't actually begin the bus cycle yet. We have to wait until T1 because the bus is busy. But if we look at our BIU state, we're in prefetch state because we made a decision to do a prefetch up here on the end of T2. And we didn't indicate to the BIU that we would be switching to the EU bus state. So what happens here is that we have a prefetch abort. Since we requested a bus transfer on T4, we can abort the impending code fetch, which happens on the next cycle here. We begin a bus abort of 2 cycles. These 2 cycles are simply the time it takes for the EU to transition from prefetch to the EU BIU state. And then as soon as that is complete, we can begin our M cycle. Now, you'll notice that the M cycle has a wait state, so it's actually 5 cycles long. The IBM PC and XT motherboards introduce a 1 wait state for every I/O operation. So you'll see this when you look at bus traces for I/O operations, I/O reads and writes. They'll all have 1 wait state. If you're looking at a cycle trace from the Arduino 8088 project that I have, you will not see those wait states because that CPU is not connected to a motherboard and there's nothing introducing those wait states. Although I do plan to make that a configurable option in the future. And you could always set 1 wait state universally. So what we have here is that we have the I/O lines from the IO 288 light up, showing advanced I/O write and write signals. When the write signal is live, we can see the bus holds the value of 12, which is what we stored in AL up here and we're now writing to the IO port. So that's our value of AL. And then we can see that we actually end the execution here on RNI on this cycle. You'll notice that we're still in TW though, we're not in T4. So how can we end it? Well, a write doesn't need to do anything with the value that is written. So the actual execution of the write can end on T3 or the last TW cycle. It doesn't need to stick around for T4. So what we see is RNI goes ahead and reads the next instruction byte, which was B8. It was sitting in the queue. It was already prefetched, so we didn't have to wait for it. That means that the move instruction can happen on the very next cycle. And this process just basically repeats over and over and over again. Now there's some interesting things that happen. If we look at what this out was doing, this was actually resetting timer channel 1. And we'll see that here. When our out becomes TW, this is actually the cycle in which the timer channel 1 reload value is actually set. And that will start a 72 CPU cycle loop in which timer channel 1 is counting down. And then if we come back to this column, this is our DMA debugger. This is actually showing the value of timer channel 1 as a timer counter and the cycle scheduler counter. So this would actually have started up here as 18 and 72 respectively. But this isn't updated until the end of an instruction. So it's too late to see it here, but at the end of move AX, we get an update for these values, and we see that the timer is now counted down from 18 to 16, and it is counted down from 72 CPU cycles to 64. And this is simply one number multiplied by 4, but the second number is updating per cycle, whereas the first number is only updating at the end of every instruction. So let's keep going. As soon as we watch this count down to 1, when we hit 1, what happens, since the pit channel 1 is in mode 2 rate generator, the output goes low on a 1 and then immediately goes back to high, which issues a DMA request because the output of timer channel 1 is connected to the DMA channel 0. So this starts the DMA cycle, which we proceed through the DMA state machine from direct to hold request. Then the motherboard processes the current state. We're in T3, so we are accepted into the hold acknowledge state. Now the 802 to 88 bus outputs are disabled, and the wait states are started to be inserted. Well, actually, more specifically, the ready line is deasserted. So we go through S1, S2, S3, S4, and the ready line is still deasserted. So we have 1, 2, 3, 4, 5 wait states inserted by the DMA controller. So this is interesting. We'll notice that we have basically 4 wait states or 4 cycles in which the ready line is deasserted after S4. So it's not a case where we always have 6 wait states. It's the overlap or the intersection of the DMA ready deassertion and any potential bus operation that might be occurring determines how many DMA wait states you'll actually encounter. Again, I have a blog article on DMA timing, and I will link that in the description below. Not sure there's anything else that's particularly interesting here. It just continues to repeat over and over and over again. On the tab below here, I do have another tab where it has instructions basically showing the address of every instruction, the cycle number in which it occurs, and the number of cycles in which the instruction took. Let's talk about instruction timing, because that can be a little philosophical. Take this random OR instruction. This indicates that RNI occurred 1, 2, 3, 4, 5, 6 cycles after instruction execution began. But RNI itself took 3 cycles. So how do you count an instruction cycle time? Is it this value or is it this value? Because if there was an interrupt, the instruction would end here and the interrupt would be processed. But if there's no interrupt, then the instruction has to fetch the next instruction. So in theory, you could think of an instruction's timing in either, way, to the end or to the start of RNI or to the end of RNI. It's kind of philosophical. I find it interesting to count instruction cycle times from first byte fetch to first byte fetch, just so this value here, just for simplicity. Let's see if there's anything else that really needs to be said about all this. If you have any questions, put them in the comments below and I will answer them. Let's look at one last thing. There is an interesting delayed state that we can see. This occurs when the prefetcher is attempting a code fetch at the end of T2 and the queue status, the queue contents are 3. Now there's 6 numbers in here, but as far as bytes go, these are hexadecimal representations of 3 bytes. When a code fetch is occurring and the queue length is 3, then we actually delay the next fetch by 3 cycles, and we can see that happen here. This is kind of a strange scenario, but you have to model it to have accurate bus simulation. And let's see, here's another interesting scenario. We had 3 delay cycles for our next fetch, but when the fetch occurred, the queue was actually full, so the fetch could not occur. So what happens in that scenario is we transition the BIU state to idle. And this is kind of a state that's sticky. As long as the queue is full, we will stay in idle. But what happens is that the idle state cannot do any operations. It has to transition to one of the EU or PF states before it can do anything. So we'll notice here, we have a bus begin. The EU has requested a bus operation, but we aren't able to service it because we have to transition from the idle state to the EU state. So we spend 3 cycles doing that. And then, only then can we begin the 4 T cycle, M cycle, a memory write operation here. Again, this is all described in my BIU state or prefetch algorithm blog post, which is in the link in the description. So we'll see some of those idle states here, and this is how we get out of the idle state. So we actually read a byte out of the queue at this point, which means that we can now transition from the idle state to the prefetcher state because we have room in the queue. But it takes 3 cycles to do so. And we can see that we've scheduled a prefetch to occur as soon as we're done transitioning into the prefetcher state. And then on the next M cycle, we begin that code fetch. So hopefully you can see, using these 2 synthetic columns, my BEU logic and my prefetch logic, these are up to you to determine how you want to implement them in your emulator. You don't have to use the same terminology or the same statuses. But this just shows you what's going on in my brain when I am thinking about how to handle the BIU states. Anyway, I hope you found that helpful. And again, if you have any questions, either post them here or over on Bogons. Thank you.